All right, taking a look at quiz 5 from unit 3, the key here. So naming Z alkene, so you need to know what that means. Z same side. It's a hex 3-ene, so what I usually start to try to do is draw the parent name out first. So it's hex. All right, so you could have done it 1, 2, 3, 4, 5, 6. 3-ene. That means at carbon 3 we start the alkene, and there's a methyl at 3 as well. And then I like to just check to see what I made, E or Z. So if I look at this, this has higher priority, this has higher priority. Right? If I cut the alkene in half, right, this one versus this one wins. H versus carbon, this one wins. So this is actually the E version. So it's fine, it's just not what we wanted. So I just need to switch around the methyl and the ethyl, and I make the Z version here. So for this one, you're given the structure, and so you got to realize the parent chain is a cyclohexene, and you want to have your alkenes, it's a diene as well, have the lowest numbers possible. So basically, you can either start here as 1, or you can start here as 1, right? Because it could be 1, 2, 3, 1, 3 alkene, 1, 3 diene, or it could be a 1, 2, 3 diene. So the reason I chose this as 1 and not this, right? So either way I have to go through, right, to get both alkenes to have as low as number possible. I chose this one because with this one I also have a methyl that has a 1, and that gives me the lowest number possible for my substituents. So 1, 2, 3, 4, 5, 6. Cyclohexadiene, 1, 3, 1, 3, where my pi bonds start. 1, 3, cyclohexadi, because there's 2 of them, ene. And then I have 2 substituents, 2 methyls, so it's a dimethyl. And they're both on carbon 1 and 6, so it's 1, 6, dimethyl, 1, 3, cyclohexadiene. All right, so problem 2, I did ask you to add lone pairs and formal charges. So that's one thing, right? Doing careful reading of instructions is important. So all the lone pairs on everything, and the formal charges on the chlorines. Then ask for draw mechanism arrows. So again, this is showing you the things that need to happen, right? So this is very similar to some things we've worked on, right? So I'm showing you here, you have a pi bond and HCl, so you should recognize that as a hydrohalogenation. You're adding H and an X, and the X this time is chlorine. Pi bond reacts, you're going to make the more substituted carbocation secondary. You're going to do a hydride shift to get a tertiary carbocation. You can't make the carbocation any more stable at that point, so then the chlorine is going to react. It's going to add in right there. Numbering your atoms is always helpful, but you were kind of shown along the way what arrows to do here, what needs to happen. All right, give the mechanism and products for the reaction below. So again, you see the alkene, you see Br2, you see no polar protic solvent, you need to think halogenation. So that means you're going to add 2 bromines. They're going to be anti to each other, right? So those are all the things, and the second bromine is going to add at the more substituted carbon, right? So those are the things you've already started doing that you should be thinking about. So first step, 3 arrows, pi bond reacts, bromine bond breaks, bromine comes back around and reacts. It's that first syn addition, right? So you see the wedges and hatches, the bromine's kind of sitting there from the top. It would also come from the bottom, but I'm just showing one version of this. The second bromine comes in, and you notice how it goes to the more substituted carbon, right there, SN2 like, breaks the carbon-bromine bond, right? And then at this point, you can see the 2 bromines are trans. You see that stereochemistry. And then you ask yourself, did I make an asymmetric center? Well, I added bromine to this carbon, but it has 2 H's, so that's not an asymmetric center. Added bromine to this carbon, and it has an H, a tert, butyl, and a methyl. So I must have made an asymmetric center there. So this does make an asymmetric center. If it makes an asymmetric center, you're going to get both an antimer, so I had to put plus an antimer here as well, because I did make an asymmetric center. Something that's sp3 hybridized, bonded to 4 different things. All right. See mercury. You know it's oxymercuration, demercuration. Make sure you check out the solvent, the polar protic solvent that it's using. That's what you're going to add. So you're going to add an H and whatever the solvent is. NaBH4 is just there to remove the mercury, change mercury into H. So I see mercury, I know it's Markovnikov. The regioselectivity is Markovnikov. So whatever solvent I'm adding, the classic way is water, is going to be on the more substituted carbon. And I know that the solvent and the H are going to be trans to each other. All right, so again here, the OH, because it's water, ends up on the more substituted carbon. There is an H there that's trans, but we don't see it. And I had to put plus En because I made an asymmetric carbon. This carbon's bound to an H, a methyl, a terp-butyl, and an OH. So this, I made an asymmetric center, so I have to talk about the enantiomer as well that gets made. Over here, now you see BH3, you should immediately think hydroboration and oxidation. If you're thinking that, you think anti-Markovnikov for the regioselectivity, and you think syn addition. Don't need to worry about the stereoselectivity, I guess, here, because again, there's two H's there already, so you can't really see it. But the boron adds to the less substituted carbon. In the second step, that boron gets replaced with an OH, so there it is, anti-Markovnikov product, anti-Markovnikov regioselectivity. We don't need to worry about enantiomers here because, again, did we make an asymmetric center? We did not, so we don't need to write it. All right, last one here was just draw the mechanism for step 1 for the BH3. So that's just the 2 arrows, right? You show the boron with an empty p orbital, pi bond reacts, the H goes there, and you need to show that it's a syn addition, right? And I'm showing the boron come from the bottom, boron and the H come from the bottom, but it could have also come from the top. And then the second step, you replace the boron with an OH. So this is all I was looking for here, was that first step, syn addition, those 2 arrows, to show this anti-Markovnikov type reaction.